Hello and welcome to our second video on equilibrium. In this video we'll focus on strategy for working on equilibrium questions we'll see through the course of the unit and beyond. So first things first, before we jump into the strategy, I just want to mention that we do have a calculated strategy for handling questions when the system starts to move. And we have to have a coordinated effort, and so please make sure you're following some coherent steps in making sure that we answer these questions with skill. First and foremost, you have to start from a balanced equation. This is no different from any other component of chemistry. We have to have a balanced reaction so our stoichiometry works out. Um, Sometimes it's going to be written as for example, a general reaction. It may not be net ionic. Sometimes you'll need to write a net ionic equation to do that. You always want to work out any stoichiometry issues within the question prior to working out the equilibrium. So know that that's possible, that you may need to work on stoichiometry first, some very simple dimensional analysis, or solving for moles, or solving for a molarity because your volume isn't 1 liter. There's lots of reasons you'll need to play around with stoichiometry first. So start from a balanced equation. Then you'll set up your equilibrium expression. You already know how to do that. That's your Kc is equal to your products over reactants to the power of their coefficients. If you can't visibly tell what a system should do next, you want to solve for a Q, provided you're given data. So you're going to set up what we're going to call a rice chart or an ice chart. The name is not important. The organization within is very important. So we're going to set the chart up that allows us to look at initial concentrations, the changes that the system undergoes, and then the final concentrations in the system. Finally, we'll substitute those concentration values into the equilibrium and solve for an x, an unknown value, and then we'll check our answer to make sure it makes sense. So a note about our systems, our resultant math that comes from these setups often looks like a quadratic equation. And so because of that, and the College Board not giving us a math test, that's not their goal in chemistry, to give you a math test, in the scope of the AP exam, you won't be expected to use the quadratic formula. In this course, you will, and that's because in chemistry beyond this course, which is important for most of you, you need to have this skill of understanding when and when not to neglect the x. And you'll see what that means when we come to it. But for now, I want to give you a definition you can stick with. We can neglect an x value in what appears to be a quadratic formula setup when we go ahead and neglect it, calculate our x value. If it is less than 5% from what we were going to add or subtract from or to, then we can neglect it and move on with our answer. However, if that value we get is 5% or more of what we were subtracting or adding to or from, then we need to go back and run through the quadratic equation. So don't expect to see that on the AP exam, but do expect to see it in this course. So here we have an example. We have a system set up to say Kc for this reaction at 700 Kelvin is 5.10. So it's greater than 1, so we would think at equilibrium we have more products than reactants. Consider an experiment in which 1 mole of carbon monoxide gas and 1 mole of water are mixed together in a 1 liter flask at 700 Kelvin. Calculate the concentrations of all species at equilibrium. So in this system, we would need to have a Rice equation. So we're going to start off by just putting our reaction together, and note that this merciful reaction has coefficients of 1. Our initial concentrations are given. We would expect logically that our system is immediately going to proceed toward making products. That's not the question. The question says calculate the concentrations of all species at equilibrium. So we have to, in our mind, allow this to come to equilibrium. So this is where it's important that you make the understanding leap. We have initial concentrations of 1. We don't know how much product we're going to make before we reach equilibrium, but our 5.10 K value is going to guide us there. So we know that we're going to lose some quantity of carbon monoxide and water in a 1-to-1 ratio because they have the same coefficients. And we're going to gain that same quantity of carbon dioxide and hydrogen in terms of moles. So our change is going to be subtract some unknown x value from carbon monoxide and water, and we will gain that same quantity in terms of moles in carbon monoxide and hydrogen. Now again, this is molarities we're dealing with. We have a 1 liter flask. We didn't have to do any introductory stoichiometry because we had 1 mole, 1 mole, and 1 liter, which makes these values very easy to get. Sometimes you'll have a 3 liter flask, or not so tidy numbers in terms of moles. You'll need to adjust for that. Finally, what we do to reach our equilibrium expression here for each individual substance in the reaction is we will take our initial and add our change to it. So our equilibrium value of carbon monoxide will be 1 minus X, same for water, and then our equilibrium value for carbon dioxide and hydrogen will also be X. So we can then take our equilibrium expression here and we can add in our equilibrium expressions for each species. So since we have a very tidy equilibrium, we can simply plug our values in and we get these. Now, this happens to be a perfect square because these values are the same. So because of that, we can simply square root that and then square root the top, and that leaves us with our answer, this equation here. So if you were to plug all this into your calculator, you would get an X value of 0.69 molar. Now that's the final value of the molarity of carbon dioxide and hydrogen. That's one thing. You also need to find the concentrations of carbon monoxide and water, which is 0.31. I just subtracted 0.69 from 1 in my head to get the concentrations of water and carbon monoxide. And this is how it expressed my answers. Now, we did not end up with a set equation for our K expression, our K equation, that led us to believe we needed to do a quadratic equation. We'll get to a point where we see that. So let's move forward. Neglect this for now. We'll come to it in a minute. Calculate the number of moles of chlorine produced at equilibrium in a 10-liter vessel when 1 mole of PCl5 is heated to 250 degrees Celsius. Now, I know that this reaction isn't given here, so I would expect if I were you to be given this reaction. But before we do anything, we need to get the molarity of our phosphorus pentachloride. So there's our reaction. And again, this would be given to you. I don't expect you to know how to decompose PCl5 into PCl3 and Cl2 without just simple logic. So that's not testing your understanding. That's making you guess, and that won't happen. So expect to be given a reaction like this. We did a little bit of stoichiometry to get the molarity of our initial concentration of PCl5. So on our initial equilibrium, we're going to have our initial set of points. We have a non-equilibrium system that has 0.1 molar PCl5 in it. And then we're going to allow it to react. We would expect some unknown X value to be subtracted from 0.1, and then since these are all equal molar, that same quantity of PCl3 and Cl2 enter our system. Okay? And these values are 1 because these all have 1 coefficients. And so our equilibrium conditions are 0.1 minus X, X, and X. So, when we plug our equilibrium values into our equilibrium expression, which here's our equilibrium equation here, and here is our Kc, 0.041, we would come up with this, okay? And when I mentioned the negligible X earlier, this is the X I'm speaking of. This X may or may not be neglected because we don't know what its value is. So the way we determine if it's okay to do this is we go ahead and solve for X, neglecting this. And so our equation ends up being 0.041 is equal to X squared over 0.100, assuming this X is a very small value. Okay. So if we solve for X that way, we get 0.064 molar. Okay. If we compare 0.064 to 0.100, it is greater than 5% of 0.100. And that's the math you're going to have to do on your own. But 5% of 0.100 is 0.05. 0.064 is greater than that, so we cannot neglect the X in this scenario. So we're going to have to build a quadratic equation. So let me show you, if you've never done it before, how to do that. So we're going to take this equation that I'm boxing right now, and we're going to simplify it into a polynomial equal to 0. So here we go. Essentially what I've done here is I've built the polynomial into an a squared bx minus c, in this case, is equal to 0. And those values, a would be the coefficient on x, b would be the coefficient, sorry, a would be the coefficient on x squared, b would be the coefficient on the x value, and c would be this number. So those values get plugged into the quadratic formula. And then we solve for x, And in this scenario, we get two values for x. We're not going to get a negative value for x. That's not possible, obviously. You can't have a negative molarity. We get a x of 0.047, okay? And I want you to note the difference, and this is the molarity of our x value, between that and what it would have been had we neglected x and left it that way. That's a significant difference. And that is the reason that sometimes we can and sometimes we can't neglect x. Now, that should also lead you to believe that sometimes we're going to neglect an x that may give you a meaningful difference in our resultant x value. However, on the College Board AP exam, you won't have to do that, so you're going to roll with neglecting the x, okay? In this course, you're going to abide by the 5% rule. If it's 5% or greater, you're going to not neglect the x. If it's less than 5%, you can neglect it. And the answers will be accordingly scored, okay? So the question didn't just ask for the molarity of our x value of our resultant PCl3 and Cl2. It asks for calculate the number of moles of chlorine produced. So here's our chlorine value at the end at equilibrium is just x in terms of molarity. So we had 0.047 molar chlorine gas in our resultant system. We'll multiply that by 10 liters to remove the liters from molarity, and we get 0.47 moles of chlorine gas. So we had a little bit of stoic to do, a little bit of conversion at the end, but that's it. Another question. Two hydrofluoric acid gas molecules are broken down into hydrogen and fluorine gas, where here is our K value at some high temperature, but know that it's steady. Therefore, our K is steady. In an experiment, 5 moles of hydrofluoric hydrogen fluoride, let's call it hydrogen fluoride in this scenario because it's not aqueous. Hydrogen fluoride gas, 0.5 moles of hydrogen gas and 0.75 moles of fluorine gas are mixed in a 5-liter flask. Notice we have moles and liters. That's why we're not going to do a pressure K expression or K equation. And then we allow it to reach equilibrium. Will the concentrations of the products increase, decrease, or remain the same when equilibrium is reached? So since in this system we were given values for all three at the beginning, we have to use our K value to find out if we are going to expect our system to build more products or more reactants. Okay, so hopefully you can identify this type of question right now and say, oh, this is just a Q versus K argument, because we have values for all three. Whereas in the last couple questions, we have only had reactants, we're allowing it to come to equilibrium, and we're making a determination based on that. This time, we've got values for all three of our reactants and products, and it's just asking us if we're going to get products to increase, decrease, or stay the same when we get to equilibrium. So basically, the question is our Q for this scenario, is our Q for this set of reactants and products greater than, less than, or equal to K? And we know how to do that. So we're going to do a little bit of stoic, because our volume of our system is 5 liters, and that's not 1, so make sure that we get proper molarities to begin with. And so here those are. Once we get those three, we can then build our equilibrium expression or equilibrium equation, our Q value, our reaction quotient equation, because we don't know if we're at equilibrium or not, and we plug and chug. Notice the square here on hydrogen fluoride gas. Didn't get squared there. That's a mistake, but you know 1 squared is 1, I hope. Since our Q value, 0.015, is greater than K, 0.01, our reaction is going to shift left and produce more reactants. So our concentration of products will decrease. Okay? So, moving on to the next bit. Hydrogen sulfide gas being decomposed into hydrogen and sulfur. Diatomic sulfur, don't fall in love with that. That's not a real thing. That's just for simplicity's sake in this question. When heated, hydrogen sulfide gas decomposes according to the equation above. A 3.4 gram sample of hydrogen sulfide is introduced into an evacuated rigid, meaning it can't expand, 1.25 liter container. The sealed container is heated to 483 Kelvin, and this number of moles of sulfur is present at equilibrium. First, write the expression for the equilibrium constant Kc for the decomposition above. So just to ground you in this question, we're given a mass of this stuff to start, okay? And then we get an equilibrium value for the sulfur at equilibrium in terms of moles. We can't work in moles. We're going to have to do a little bit of dimensional analysis first to make sure we straighten everything out. But the question it's asking is first to write the equilibrium expression. So let's do that. There it is. Notice the hydrogen and the hydrogen sulfide gases are squared because of the molecularity in the reaction. When heated, oh sorry, same question. Part B, calculate the equilibrium concentration in terms in molarity for the following gases, hydrogen and hydrogen sulfide. At equilibrium, we already have the number of moles of this. Since our volume is fixed at 1.25 liters, that's the volume for everything. So we have a little bit of work to do to find out, first of all, how many moles of hydrogen sulfide we started with, and then we can start doing some fun rice tabling. So the first thing I do is determine the molarity of the hydrogen sulfide we started with. We find the number of moles, we divide by liters, we get 0.0798 molar. Then we find out the molarity of the sulfur gas in the products. So we have a beginning or initial value for the molarity of hydrogen sulfide and a final value for molarity of sulfur S2. So we're going to build a Rice equation. Here we go. We still have our reaction. Our initial concentrations, based on our stoich, told us we had this molarity of hydrogen sulfide to begin with. Now, this is a great example where we have coefficients other than 1 to begin with. So we're going to have to stay tidy here. So note that because we know we're going to make products in some quantity, we're going to lose some quantity of reactants according to the coefficient. So it's minus 2x this time. Okay? We're going to gain 2x in terms of hydrogen and gain 1x in terms of sulfur. And then finally, these are our equilibrium final values. Notice, though, we already know x because sulfur concentration in the equilibrium system is this. So since we already know x, 0.0298, we can simply plug that value into our equilibrium expressions for hydrogen sulfide and hydrogen, and we have the answers requested for part BI and II. So our value for hydrogen is 0.0596, and for hydrogen sulfide is 0.0202. Please pause if you need to go back through that. So part C says calculate the value of the equilibrium constant for the decomposition reaction at 483 Kelvin. So we were never given a K in this scenario. We didn't have to even worry about it. But we now have equilibrium values for all three species. We need to include their exponents from our equilibrium expression, and there's our K value for the reaction at 483 Kelvin. And finally, calculate the partial pressure of sulfur in the container at equilibrium at 483 Kelvin. Now you might be thinking, oh my gosh, I have to work back through a Kp to find partial pressure sulfur. No, you don't. You already know the number of moles of sulfur present in the system. You know the temperature, 483 Kelvin. Sounds a lot like a PV equals nRT to me. We have a volume, 1.25 liters. We have R. All we need to do is puvnert. So here we go. Calculate PV equals nRT. Our final pressure for only sulfur. Okay, we have moles, we have volume, we have temperature. Our final pressure is 1.18 atmosphere. So for the reaction, hydrogen plus 1/2 mole sulfur makes 1 mole of hydrogen sulfide at 43. Calculate the value of the equilibrium constant Kc. This is an example of using our skills of how we can handle a manipulated equilibrium reaction. This is the same reaction as this. It is reversed, and its coefficients are halved. Okay, so in light of that, since it's reversed, Kc prime is 1 over Kc square rooted, or to the 1/2 power, because our coefficients are all halved. So we plug our values in. Our Kc for that reaction, as it's written here, is 1.96. And that concludes video 2.